Okay, in this lesson, we're going to go through drawing log graphs and using log scales as part of the data presentation interpretation module. The aim of the lesson in general is that students will be able to draw a graph using a logarithmic scale and any adjustments we might use using logs when provided with a linear exponential relationship. But that's for a bit later on in general. We're going to start by transforming exponential relationships into a logarithmic relationship by expanding expressions using the laws of logs. So we're going to go through the laws of logarithms and use those first, and then we will use it in transformation. So in general, most of the graphs you've seen so far have axes labeled like this. We have along the bottom, the gaps between the numbers in the bottom go steadily up. If I wanted to describe that in more detail, I would say that there is an increase of 10 each the way along. And many of the graphs that we've done so far, whether cumulative frequency or frequency polygon, etc., will be of this form. This constant increase, or an addition along this axis, is called a linear scale. This has many uses that we've seen, but sometimes it isn't a good fit. Consider the table of values that we have below. We have x values of -2, -1, 0, 1, 2, and 3. And then we have y values, essentially a function of x values, of a quarter, a half, 1, 2, 4, and 8. Now if I just plot those using the scales that we have had beforehand, like in a linear scale. So where we have a 0, 0 here, and we have a -1, -2 to the left, and a 1, 2, 3, etc. to the right of that, I'm going to plot -2 a quarter. A -2 a quarter will be 2 to the left and a quarter of the way up roughly there. Then if I go to -1 a half, I will go to here. 0, 1 will be there, 1, 2, 2, 4, and 3, 8. Now if I was to draw a line through that, you can probably see that we're struggling already to fit points on this graph, and in fact the fourth one will go to 16, the fifth one will go to 32, etc., etc. And as such, a linear scale doesn't suit this graph. In many ways, it actually gives us less things to measure, as we'll see later on in the lesson, and that's ultimately why it's not as useful a scale. But how about if we label our axis something a bit like this? So instead of having 0, 10, 20, we still have 0, then 10, but instead of 10 we go to 100, and then we go to 1,000, etc. I've used 10 to the 4, 10 to the 5, 10 to the 6, just to say I'm going to multiply 10 4 times together, 5 times together, 6 times together. It stops me having lots and lots of zeros around there, which can get visually confusing. If we go to analyse the gaps between the numbers at the bottom now, we can see that instead of being adding by 10, or a gap of addition by 10, it's a gap of multiplying by 12, and as such that horizontal axis will go up much more quickly. This constant increase in multiplication along its axis is not called the multiplicative scale, but it's called the logarithmic scale. It's important to note that the gap between the numbers still needs to be constant. So as in the one before, it was an addition of 10, this one's a multiplication by 10, but you shouldn't like multiply by 10, then by 5, then by 20, by 10. It always has to be the same as we're going along if the gaps between them are exactly the same. So why is this important? Well, basically the graph that we've just looked at goes up and off the graph scale very quickly. It's difficult to use for any kind of measurement, and this removes some of the effectiveness of the graph itself. So we don't really want a graph like that. It's not easy to measure. We need another set of mathematics in which to measure it. But if we use an effective logarithmic scale, we can draw a graph that is proportional in nature. You may call it a straight line. So if we get our relationship set up well at the start, we should get a graph like that, and graphs like that are much easier to both measure, draw, and analyze. We'll come back to that more at the end of the lesson, but for now that's enough for the setup. We are going to look at the laws of logarithms. Well, if we could turn the graph from the first one into any graph like the second one, we'd be able to use whichever graph suited our needs. We could use the linear one where applicable, the logarithmic one. And we're going to need some very cool mathematics that you may not have seen before to do it. Now, as it turns out, there's people much smarter than you and I that discovered this or invented this a long time ago, so that we wouldn't have to. We just need to be able to apply it. So a logarithm can be basically seen in your calculator. So it has, on the Casio model that I've got here, it has 3 buttons that have logs. 1, 2, 3. And they're grouped together. I'll start with the one on the top right, which says log, and then a gap, and then a gap. In the case of the first gap, it stands for the base, and the next one is the number. Now, for the base, we are only going to look at applications which have log to the base 10 or a natural log. For the first section, I'll just do log to the base 10. Log to the base 10 of 100, what do you get? Well, basically this question is asking what power of 10 must I raise it to so that I get 100. But if I just type that into the calculator, log to the base 10 of 100, that's as much as you need to do. As it turns out, this log button to the left actually is shorthand for log to the base 10, because log to the base 10 is the most commonly used one, because it happens to match the way that we count. So if you hit log 100 and hit equals, you should get the number 2. And if you do, we're good enough to go on to the next stage. Here are some ones for you to try. Log 64, log 24, log 100, again, log 1000. You might be able to estimate before you calculate, especially C, since we just did it in the previous slide. The LM button, or natural log button, is a special type of log that we'll come back to later, and I seem to be saying that an awful lot, but that's true. Logarithms are actually the inverse or the opposite of indices or powers. So you may have heard me say before that all operations of mathematics have an opposite or an inverse or a way to undo it, if the case may be. Common ones you're familiar with would be the opposite of addition is subtraction, the opposite of division is multiplication, etc., etc. In this case, the opposite of taking the power of something is to take a logarithm, and the rules that we've got here will help you calculate with logarithms. The answers that you should have got for the log 64, 24, 100 and 1000 are displayed on screen. So we're going to look at 3 laws of the logarithms, and at the core, logarithms are a way to take multiplication problems and make them addition ones, and vice versa. So let's look at the first one. It's called the product rule, and I'm going to show you it through an example. So it's log to the base 2 of 5, log to the base 2 of 6. There is no need to worry about what log to the base 2 means. I have just included it in the question to show you that this only works if these two logs bases are the same. So in this case it worked because 2 and 2 are the same. It would only work if 3 and 3 were the same. As long as the two bases are the same, this rule will apply. If I was to show you the formula from like a formula book, if you want, it would be log to the base a of x plus log to the base a of y equals log to the base a of x, y, which in short is a fancy way of saying that if we have logs of the same base that are added, we can combine this into one by multiplying. So if I take the example that we have there, log to the base 5 plus log to the base 6 would be the same as log to the base 5 times 6. And 5 times 6 gives me log to the base 2 of 30, and you can just leave it like that. That is our first law of logarithms that we're going to see. The second law, you might be able to guess already. It's called the quotient rule, quotient being a funny or fancy name for dividing. So we're going to simplify log to the base 4 of 48 minus log to the base 4 of 6. Again, I've just included a base 4 to show that this will work as long as these two things are the same, or they have the same base, in this case 4. In shorthand, the formula version of this looks like log to the base a of x minus log to the base a of y. We can combine this as log to the base a of x divided by y, or in short, if we have logs of the same base that are subtracted, we can combine this into one by dividing the first one divided by the second one. And if I do it for log to the base 4 minus log to the base 4 of 6, that's log to the base 48 minus log to the base 6, or log 6 is 48 divided by 6. And when you combine those together, that will be log to the base 4 of 8. That's 2 of the rules down. Fairly straightforward and nothing too fancy about any of that. If I go for the third one, it's called the power rule. And the problem that I'm going to put up here for simplifying is 3 log to the base 3 of 5 minus 2 log to the base 3 of 8. Again, the base 3 is only there to show that the two bases must be the same for this to work. Now, you might spot that there's a subtraction between these. You may think, well, I can just divide the two of them, and you would be partially correct. The problem is that there is a 3 in front of this log and a 2 in front of this log, and we need to somehow make it part of the log before we perform our quotient rule or subtraction rule. And thankfully there's a rule to do that. The formula version looks like this. B log x becomes log x to the power of b. Essentially this b, the number that gets multiplied in front of the log, becomes the power of the number at the end. So 3 log 5 becomes becomes log 5 cubed, and 5 cubed is log 125. 2 log 10 becomes log 10 squared, and that'll be log 100. And if I write them like that, then I can combine them using the quotient rule, or log to the base 3 of 125 minus log to the base 3 of 100 is 125 divided by 100, which would give me 5 over 4 in a fraction, or 1.25 as a log. That's as much as we're going to do in this first part. I hope that makes some sort of sense, because you can complete the logarithm sheet that I've attached as well. At the bottom, there is a second set where you will use the laws of logs in reverse. So if I have two things that are multiplied together, we can split them apart as addition. If I have two things that are divided by each other, I can split them apart as subtraction. Give those a go and let me know how you get on.